Ryan Seacrest here. When you have a busy schedule, it's important to maximize your downtime. One of the best ways to do that is by going to ChumbaCasino.com. Chumba Casino has all your favorite social casino games like spin slots, bingo, and solitaire that you can play for free for a chance to redeem some serious prizes. So hop on to ChumbaCasino.com now and live the Chumba life. Sponsored by Chumba Casino.
No purchase necessary. VGW Group. Void where prohibited by law. 21 plus. Terms and conditions apply.
Hi there, welcome to episode 7 of The Logic of Risk. I am not one to repeat myself, but I want to thank you all for following these podcasts with so much interest. Given the topics we have covered and the abstract nature of these early episodes, it definitely wasn't a given that you would stick around. And if this is your first time listening, first of all, welcome. I highly recommend checking out the previous episodes to get introduced to many of the terms and concepts we use, especially if they are new to you. You can find these podcasts on all major platforms. On YouTube, you can also find transcripts of what I say in case anything is unclear. Today, we are still talking about probability, but we are going beyond the classical and frequentist definitions. We are going to dive into the propensity perspective, and it's going to be an important test for this podcast because, frankly, propensity theory is less intuitive than what we have seen so far. It might seem unnecessarily complicated, and maybe it is, but it's a really important objectivist attempt to define probability. Plus, in certain fields, it actually can be a pretty solid point of view. I will do my best to make it clear and show where and when it could make sense. Remember, the classical definition sees the probability of an event as the ratio between the number of favorable outcomes, that is, those in which the event occurs, and the total number of possible outcomes, assuming all outcomes are equally likely. The frequentist, on the other hand, defines the probability of an event as the theoretical limit toward which the relative frequency of that event converges if you observe your random phenomenon an arbitrarily large number of times. In previous episodes, we discussed the limitations of both definitions. The classical definition is so limited that it only works in idealized situations or for simple games of chance, so it is not really useful for risk management. The frequentist definition, meanwhile, is great for describing the probability of large-scale random phenomena, but isn't suitable for one-off events. And even when studying mass random phenomena, there are some caveats. To reliably calculate relative frequency, we need good data. And by good data, I mean not only data of satisfactory quality, which goes without saying, but also in sufficient quantity. Determining just how much isn't trivial, and we will come back to that soon. It can range from a few dozen observations for fairly regular random phenomena with limited variability and almost negligible extreme events to several thousands or even millions and billions for more erratic and volatile phenomena that might feature non-negligible extremes. Unfortunately, or maybe fortunately from a scholar's point of view, it is the latter type of events that have the biggest impact and are therefore of most interest in risk management. Estimating relative frequencies for a highly erratic phenomenon based on scant data and taking them at face value is just plain foolish. In our last episode, we also introduced the problem of historical bias. Historical bias pops up when we mistakenly assume that the past is a great predictor of the future, and that if we have enough data, we can expect the future to mirror the past. Our job then becomes simply to estimate the probability distribution, and then we are done. For those of you familiar with bank risk management, you know that this is unfortunately what gets done under the so-called Basel framework with historical simulation and stress test based on pre-observed scenario variations for market, credit, and operational risks. All of these are situations marked by non-trivial tales, especially in credit and operational areas. And then everyone wakes up in a cold sweat when the estimates turn out to have underestimated the risk. After all, if something has never happened before, why should it happen? But don't worry, the happy ending and the promotion always comes eventually. These guys usually end up becoming politicians. If you are not up to speed on bank risk management, that's fine. We will do a few special episodes on that because I believe it's essential to understand how banks decide or should decide, according to regulators, whether to grant you a mortgage or a credit card. So just wait. To explain historical bias, there are plenty of metaphors and allegories, but one is especially effective, and I often use it because it can be adapted to explain other data management issues. Having a model or approach that suffers from historical bias is like driving a car while only looking in your rear view mirror. Sure, you can see clearly what's behind you, but if you only look in the rear view mirror, sooner or later you are going to crash into something or someone. And then whose fault is it? Your model, the rear view mirror, or you for being an idiot? History will be the judge. Another useful image is that of a runner trying to set a new world record. We all agree that to set a new world record, you have to run faster than the person who held it before. That is, you have to beat the previous record. Clearly, until we observe that new record, it is not in our data. All we know is that it will be better than what we currently have, which then acts as a sort of lower or upper bound, depending on how you look at it. If we are talking about speed, it will be higher. If we are talking about time, it will be lower, shorter. So, tell me, why do we all accept this trivial fact about sports records, yet in finance, economics, or in the study of wars or pandemics, we take the historical maximum as an unsurpassable value, the worst of the worst or the best of the best that our models can predict? We are literally shooting ourselves in the foot and then complaining. But we will have time to dive into those practical details later. For now, let's focus on the definition of probability as propensity. I should warn you that some simplifications will be necessary, so my apologies to any hardcore propensionists listening. You never know. The propensity definition is relatively unknown outside the experts, but it has some interesting aspects that we will highlight. I will also mention that, from an application standpoint, the propensity view is virtually indistinguishable from the frequentist one when studying large-scale random phenomena. The difference shows up, at least in theory, when it comes to single events, cases where, as von Mises pointed out, the frequentist view doesn't really even define probability. The propensity definition, at least in its Popperian variant, should, and we will soon see why I say should, be able to study one-off events. In reality, though, that's not really the case unless you move toward that probabilistic subjectivism that Karl Popper was so wary of. Propensity theory is mainly traced back to Peirce, who, in some writings and letters around the turn of the 19th to the 20th century, outlined what we should more precisely call his dispositional view, though hardly anyone uses that term these days. For Peirce, probability is a natural disposition of things, a relational property comparable to weight in physics, which comes into play when the outcomes of an experiment or phenomenon are not certain but random. But Peirce never fully formalized his ideas. It was Karl Popper who emerged as the champion of the propensity view. For those interested, I highly recommend reading his most famous article on the subject, The Propensity Interpretation of Probability, published in 1959 in the British Journal for the Philosophy of Science. Other major figures one can meet in the propensity school includes Gillies, that we already mentioned and that we will discuss next time, Hacking, Meller, Geer, and to some extent Lewis. For Peirce and Popper, probability is something objective, measurable, and independent of the observer. It is nothing more than the measurement of the actual possibilities for an event to happen, not just abstract possibilities, but ones that are objectively and physically real. According to them, every random phenomenon is characterized by real, natural, physical tendencies that lean toward a specific outcome. These tendencies are what we call propensities. So, probability is essentially the empirical measure of these propensities. Think of propensities as relational extrinsic properties of the world around us. Just like weight, recall from school physics that while an object's mass is an intrinsic property independent of its position in space and other physical quantities, its weight, its gravitational force, is the effect produced on that mass by a gravitational field. The mass of an object doesn't change, but its weight does, depending on whether it is measured on Earth or the Moon, especially on a spring scale. Similarly, propensity, like weight, is a property that depends on the interaction with something else, and that something else is the experimental setup, the conditions around the experiment, or simply the repetition of the random phenomenon. I repeat, propensity isn't probability itself, but the presumed cause behind it. Empirically, we can measure the manifestations of the propensity, and from those measurements try to understand it better. There is, however, one fundamental difference between Peirce and Popper. As Richard Miller pointed out, Peirce anticipated von Mises in claiming that studying the probability of single events doesn't really make sense. After all, for Peirce, the way a propensity manifests and can be measured is closely linked to the concept of relative frequency, just like the frequentists. So, you need a collective and all that blah 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 from the last episode. Popper, on the other hand, who from now on will be our reference point for propensity theory, saw in propensities the possibility to study even single events without resorting to that subjectivist approach which he loathed for being unscientific, overly dependent on the individual, and therefore volatile. In particular, Popper argued that the subjectivist view would not be compatible with probabilistic calculations because it would not allow for precise enough measurements of beliefs, which are at the core of the subjectivist perspective. In reality, as De Finetti and others have shown, that isn't true at all. In fact, as I will try to show you within the limits of our current tools, it is the Popperian solution that ends up being unsatisfactory when we actually want to use probability rather than just talk about it. But before we get into that, we need to explore why Popper decided to develop the propensity view as, in his opinion, a superior objectivist definition compared to the frequentism of Venn and von Mises, even though in the end he remained somewhat of a supporter of the latter. We can do that by looking at some paragraphs from what Popper himself wrote in 1959. So, let me read to you what Popper writes on pages 26 and 27 of his article The Propensity Interpretation of Probability, which you can also find on thelogicofrisk.com. Quote, "The frequency interpretation has been often criticized, but I believe that it is possible to construct a frequency theory of probability that avoids all the objections which have been raised and discussed. I have sketched such a theory many years ago. It was a modification of the theory of Richard von Mises, and I still believe that, after some minor improvements which I have made since, it is immune to the usual objections. Thus, the reason why I changed my mind in favor of the propensity interpretation was not that I felt I had to give way to these objections, as has been suggested by W. C. Neal in a discussion of a paper of mine. Rather, I gave up the frequency interpretation of probability in 1953 for two reasons. The first was connected with the problem of the interpretation of quantum theory. The second was that I found certain flaws in my own treatment of the probability of single events in contrast to sequences of events, or singular events, as I shall call them in analogy to singular statements. Unquote. Okay, this will be the starting point of our next episode. I know you might think I'm spending too much time discussing what probability is, but believe me, this is just the beginning. And we need this knowledge. If, as Pierre-Simon Laplace once said, many of the most important questions in life are essentially just problems of probability, then we really need to take all the time necessary to understand what this probability is all about. See you next time. Ciao, ciao.
Ryan Seacrest here. When you have a busy schedule, it's important to maximize your downtime. One of the best ways to do that is by going to ChumbaCasino.com. Chumba Casino has all your favorite social casino games like spin slots, bingo, and solitaire that you can play for free for a chance to redeem some serious prizes. So hop on to ChumbaCasino.com now and live the Chumba life. Sponsored by Chumba Casino.
No purchase necessary. VGW Group. Void where prohibited by law. 21 plus. Terms and conditions apply.